So now we understood something about temperature time curve, particularly for water. We have seen this for water as an example. So now we are entering into the exact topic of what is MCP delta T. So to understand this, let's again go with a simple example. A block of ice, mass M, ice. Take this, and you have a very hot surroundings. Hot surroundings as in you can take that as 25 degrees Celsius surroundings. Surroundings, this is nothing but surrounding air at 25 degrees Celsius. So we all know that by virtue, when you are keeping it outside for some time, this block of ice, this will automatically going to supply some heat to ice. So ice will start to melt, and that is just a melting process, but in a thermodynamics point of view or heat point of view, it's a heating process wherein this ice is taking heat from the surroundings. So now, as a thermodynamic or as an engineer, so what you need to do is, how much energy is getting transferred from the surrounding to mass, or why, first of all, why you need to understand this. Think of a refrigerator or think of an air conditioning unit in your room. So what you need to understand is your father might have told you or your mother might have told you that this room needs a 1 ton AC. So how they are telling that this requires a 1 ton AC or 1.5 ton of AC? That all comes under this calculations of what we are doing, MCP delta T, all these things. So we need to know how much heat energy that we need to extract from the room and push it to surroundings. So that is where this 1.5 ton, 1 ton comes into picture. So for a 10th standard ICSE perspective, it is nothing but a simpler version of what you are trying to do in the refrigeration and air conditioning cycles. So now what is happening is this mass of ice is gaining some heat from the surroundings. We are going to quantify this in some number. How will you do that? This is based on the first law of conservation of energy, which is nothing but the 0th law of thermodynamics. So what is going to happen now is, we all know. Okay, let's go from the beginning. The energy of the universe is constant. Energy of universe is equal to constant, and we derived a second derivative of this energy of universe as constant as delta E of system equal to delta E of surroundings. Okay, which means whatever heat the system is gaining should be supplied by some surrounding or some other body. So if you are getting some heat, somebody should be supplying you heat. That is how the universe works, and that is how physics concepts works. So let's assume that this is the what is meant by specific heat capacity. So let's assume this ice is having a specific heat capacity of 2 kilojoule per kilogram Kelvin. So this is a constant value for ice at a particular temperature. So now this tells you that if I supply 2 kilojoule of heat to 1 kilogram of ice, its temperature will rise by 1 Kelvin. So this is the number that this 2 kilojoule per kilogram Kelvin signifies for a specific heat capacity. So now you can wonder, like, what if I have 2 kilogram of this mass or 3 kilogram of this mass? So you need to multiply this number by 3, which means specific heat capacity multiplied by mass will give you the heat capacity, or the total amount of heat required to increase the temperature of the substance by 1 Kelvin. And into, there is one delta T factor here coming into picture, delta T of system. Okay, so this is the specific heat capacity into mass, which is nothing but the heat capacity. Okay, so now I got specific capacity, so which means 2 kilojoule per kilogram Kelvin, which is constant for a material. So now, and I am having like m mass of a substance. So the heat capacity, that means the amount of heat that I need to give to this substance to increase its temperature by 1 Kelvin is Cp into m for this ice. But let's assume I know this temperature, so I can easily figure out like how much heat this ice has taken in. So, but the thing is, this ice might already been in some temperature, let's say T1 Kelvin, and it is increased to T2 Kelvin. So we need to consider only the difference in temperature between final and initial, so that it becomes T2 minus T1. This is the change in temperature for this ice. So now if you correlate the equation, I have raised the temperature of ice from T1 degree Celsius to T2 degree Celsius. So if I subtract T2 minus T1, which will give me the number in temperature, number of degrees Celsius that is increased in the ice. So to increase the temperature of ice through this amount of degrees Celsius, I need to supply this much heat. Okay, so if you multiply these two, will give you the total amount of heat this ice has taken, which is nothing but mass into specific heat capacity into delta T. This is the universal equation for heat transfer. Let me just give you a quick recap. You are taking a mass m of ice which is at T1 degree Celsius, and it is led to surroundings and wait for like 1 hour or 2 hours. The surrounding is at 25 degrees Celsius. So obviously there is a temperature difference, 25 degrees Celsius. This might be at T1 degrees Celsius, which is like around close to 0 degrees Celsius because it's ice. So this 25 degrees Celsius surroundings will spontaneously give some heat to this ice and make its temperature to rise from T1 degrees Celsius to T2 degrees Celsius. So what is the actual temperature difference that has changed from T1 to T2? That means T2 minus T1 is the actual increase in temperature of this ice. So if I want to increase 1 Kelvin in this block of ice, I need to supply Cp amount of heat for 1 kilogram. Okay, so if I take m kg of this substance and I want to increase the temperature by 1 Kelvin, so I will need to supply m into Cp amount of heat, and this is for m kg. Okay, so now I want to increase the temperature of m kilogram of substance through T2 minus T1, which is nothing but the change in temperature of this substance from T1 to T2. If I want to increase the if I want to increase the temperature by this scale, by this number for m kg of this substance, then what I need to supply? I need to supply m into Cp into this number. So this is the heat equation or heat transferred. This is the heat transfer equation which we'll be using to solve all the problems. So as a next topic, let's discuss about heating and cooling. So when you ask somebody to describe about heating process, right, the first thing they will tell is like increase in temperature. If you try to increase a body's temperature, then they will say that it is heating process. So if you ask me that whether that is a correct statement, I would say it's wrong statement. So why is? Because heating means supplying thermal energy to a body. So when you are supplying, for example, let's take a block of ice. If you are giving thermal energy to this, so then this means that you are heating this block of ice. It doesn't necessarily need to increase the temperature of the ice. For example, whenever you are giving some X kilojoules of thermal energy to this block of ice, it can be at 0 degrees Celsius, and it is not necessary that this ice needs to go to like water at 20 degrees Celsius. It's not the case. It can be still a water at 0 degrees Celsius, which means I am not increasing the temperature, but still this is a heating process, which means like a blind statement of heating means just increasing temperature is not correct. Heating means supplying of thermal energy to a body, which is called heating. Similarly, what is meant by cooling? With reference to the same context, if somebody says cooling means reducing the body's temperature, it's partially correct, it's not absolutely correct, because cooling means removing thermal energy. from a body. Let's go with the same context. Let's take ice now, water now. Water at 20 degrees Celsius. Okay. So now I am trying to minus of heat energy. I am trying to remove some heat energy. So for example, this can become 10 degrees Celsius, which means the blind statement is holding true here. Like somebody is trying to remove heat from this 20 degrees Celsius water, which is becoming a 10 degrees Celsius water, which is again like reduction in temperature as we generally understand what cooling process means. But let me give you one more example. Let's take 0 degree water and remove heat from this. What happens is it can form a ice, which is still at 0 degrees Celsius. This is just an inverse of what happened there. So which means somebody is giving you a 0 degree water and you are removing some kilojoules of heat from it. It is converting into 0 degrees Celsius ice. There is no decrease in temperature in this case because this is 0 degree water and this is 0 degree ice, which means it is contradictory to the common belief that cooling always means decrease in temperature. It is not the case. Cooling actually means is you are trying to remove some thermal energy from a body. Okay, now let's discuss about the types of heat transfer. When I say types of heat transfer, sometimes we will refer this heat transfer as heat, both are analogous. Sometimes we will refer it as types of heat. So there are three types of heat transfer. One is conduction, other is convection, and the third one is radiation. So as per ICSE 10th syllabus, we will be looking into only the first mode of heat transfer, which is conduction. The remaining two is like not included in your syllabus. And this but it is good to know that what these three terms means and what is the main difference between these three terms, so that you can understand more on the heat transfer modes. So in conduction heat transfer, let's take a block of ice. So you will have H2O molecules, HOH, and you will have similarly multiple other H2O molecules. So the heat transfer in a conduction process occurs at a molecular level by interaction between this molecule with the other molecules. So this conduction heat transfer will occur when there is a close contact with the body. For example, if this ice is again placed nearer to another ice which is at a different temperature. So this is at minus 5 degrees Celsius, let's say this is at 0 degrees Celsius. So the molecules of water here will transfer some heat to this molecule of H2O by virtue of close contact. So this conduction mode of heat transfer will occur only when a body is in close contact with another body, wherein there will be some heat transfer occurring by mode of conduction. So for example, if these two ices are apart, so the ice is here and this ice is here, so there won't be any conduction heat transfer occurring between these two ices. So which means in a nutshell, for conduction heat transfer to occur, which is nothing but the interaction of the molecules present in these bodies with each other, when they are coming into close contact with each other, there will be some thermal interaction happening between the molecules of the first body, the molecule of the second body, sharing the energies, thermal energies obviously. So one which is at a higher temperature will share some thermal energy to which is at a lower temperature. So again, I'm just repeating, whenever somebody says conduction heat transfer, it will occur by virtue of a body coming in contact with another body and when there is a temperature gradient, which means when a body is at a higher temperature, it comes in contact with a body at a lower temperature, there will be a conduction heat transfer happening from a hot body to, which means body at higher temperature to a body at a lower temperature. And how this conduction heat transfer is occurring is like you need to look at the molecular level. So the molecules, for example, ice, it has H2O molecules. So these molecules will be interacting with nearby molecules by transferring the heat energy. And the convection, on the other hand, convection and radiation, I'll come to radiation next. Convection is nothing but, say for example, you are having an ice and it is surrounded by air. So this air will not be stagnant. What it will be doing is it will be just moving. So whenever a body is in contact with a moving fluid, moving fluid. It's not liquid, it's a moving fluid, which means it can include liquids as well. Liquids as well as any gaseous matter. So if a body is coming in contact with a moving fluid, by virtue of the moving fluid, it will undergo some convection heat transfer when there is a temperature difference. If it is same temperature, this is a T degree Celsius and this is a T degree Celsius, obviously we know that there won't be any temperature gradient, so there won't be any heat transfer. But if this ice is at higher temperature compared to some moving fluid, for example, this is like liquid nitrogen moving here and there. So which means like compared to this ice, liquid nitrogen will be at a lower temperature, wherein heat transfer will occur by mode of convection, because this cannot be conduction, because ice is a solid body and it is exposed to a moving fluid which is like liquid nitrogen. It's moving here and there, so it will be a convection heat transfer. So now coming to radiation. So radiation is a heat transfer. It's a very interesting heat transfer which will occur by virtue of radiation heat transfer is a heat transfer which will occur in the form of electromagnetic radiation, electromagnetic waves. For example, any body which is having a temperature greater than 0 Kelvin will radiate some form of electromagnetic waves. It can be infrared, it can be like visible light. For example, if you take this light, it is emitting, it is obviously at greater than 0 Kelvin. It is emitting some electromagnetic waves in the form of white light, which is like in a visible spectrum. And so it is giving some heat. You can easily take an example of sun. So sun is radiating large amount of heat by virtue of its temperature. Its temperature is greater than 0 Kelvin, which is close to like 5500 Kelvin. It is giving out some energy in the form of electromagnetic waves, and you can feel that heat when you are in earth and you are just exposing yourself to sun. You can feel that heat. So those heat are coming in the form of electromagnetic waves, and that is radiation. And the most important difference between these two heat transfer and radiation is that radiation doesn't require any medium. It can travel in vacuum as well. That is why the thermal energy from sun is reaching earth, though there is a vacuum between sun and earth. But the conduction heat transfer and convection heat transfer will only occur when there is a medium, or it needs a medium to transfer heat from one body to another body. And if you ask me the difference between this and this, conduction heat transfer comes via contact between two bodies, and convection heat transfer will occur when a body is exposed to a moving fluid. It can be moving liquid as well as moving some gaseous matter.